Hello, my name is Kaylin Ebener, and this is my second lab, the motion of a falling object. In this presentation, I'll be discussing how I performed a real-life observation of a falling object, how I created two different computer models of the system, how I compared my real-life observation to the computer models, and then I'll discuss the principles involved. The first goal in this lab was to implement Newton's second law with a non-constant net force caused by the forces of gravity and drag. The drag force will be shown in one of our computer models and excluded from the other. We use the same position and velocity update formulas from last time to model the motion of the object in GlowScript. First, we analyzed the video tracker and then created the computer model in GlowScript. The system was a crumpled piece of paper which falls slower than the rock and has a diameter of approximately 0.0445 meters and a mass of approximately 0.00375 kilograms. The paper ball was dropped from about chest height, and next is a video of motion. I oriented the axes for the ball moving in the negative y direction by placing the origin on the object's initial position. The video is slightly skewed, so I rotated my axes to accommodate. The calibration stick is set to a known height. The video is 30 frames per second, and the program gave me the position data of the object in the tables and graphs. The graph has a slight curve in its slope, indicating the non-constant net force. The initial position and time range were obtained from the table, and we know the initial velocity of the object was 0 since it was dropped from rest. I initialized my GlowScript program to the mass, position, initial velocity, and time range from tracker. Here's the code to represent the force of gravity and the position and velocity update formulas. This is the GlowScript program with only gravity affecting the net force. There's my code. Then there's the paper ball moving downward. Then there's the position versus time graph, which has a curved negative slope as expected due to the acceleration of gravity. Then the velocity versus time graph, and then the position and time data that the model produced. To include drag force, I changed the net force to be the sum of the calculated force of gravity and the calculated drag force. I set drag equal to the coefficient of b, which is approximated through trial and error runs until the predicted final position best matched the observed final position of the ball, times the magnitude of the velocity squared, times the positive j-hat vector since the direction of drag is opposite to the direction of the object's motion. I input all this information in my code down below. This is the GlowScript program that accounted for gravity and drag running. The animation includes arrows representing the drag force, the position versus time graph looks similar, and the velocity graph still exhibits a negative slope, but is slightly more curved as if trying to level out. These are the two graphs of velocity versus time. The code without drag is on the left, and the code with drag is on the right. There are only slight differences. The graph without drag has a straight negative slope, while the graph with drag has a very small curve in its slope and the line seems to start to level out. The model with drag is the best predictor of terminal velocity. It is just not very apparent since the time of flight was not the full time needed for the object to reach terminal velocity. Since terminal velocity happens when the force of drag pointing up has exactly balanced the force of gravity pointing down, when terminal velocity is reached, the net force is 0. That is another reason why the model without drag cannot accurately model terminal velocity. There would be no force to oppose the force of gravity on the object. If the object was initially thrown downwards, it would have a non-zero initial velocity. I manipulated my program with drag to have an initial velocity of 1 in a negative y direction, and the velocity versus time graph it produced is on the right. My model was not a great representation of terminal velocity, but one can see that the velocity was starting to near negative 4 meters per second, so I took that to be terminal velocity. The graph of the model with initial velocity seems to start leveling out at negative 4 meters per second, the terminal velocity, sooner. The magnitude of the terminal velocity does not change. The time taken to reach it is just less. I created my comparison graph with the time and position data from tracker and both computer models in GlowScript. This line graph was created by first inputting the position and time data from tracker, the computer model without drag, and the computer model with drag into a spreadsheet and then plotting it into Google Sheets. The observed data is shown in the blue dots and the predicted positions are in red and yellow, without drag and with drag respectively. Each curve is similar in shape, but the model that incorporated drag has the predicted final position closest to the observed final position. Some of the divergence from the observed position could have been due to a blurred center of mass, causing mistakes when placing the points in tracker, or possibly an unaccounted for outside force causing movement in the x direction. Concerning improvements in the real-life scenario, the object could have been dropped from a greater height to allow more time of flight and a clear graph depiction of terminal velocity. Concerning tracker, a better camera with more frames per second could have been used, or more decimal places in the position values could have been incorporated for more accurate position data. To improve the computer model, the calculation for drag force could have been tailored to the object for the most accurate depiction of motion for the specific object, possibly by incorporating the object's specific dimensions. In this lab, our main objective was to use Newton's second law when the net force is non-zero due to gravity and drag to model the motion of a falling object, the paper ball. Overall, we learned how to use Newton's second law with constant acceleration to model motion, how to account for the drag force, and how to identify the terminal velocity of a falling object. Thank you for watching!